In this video, we're going to learn to do a proof by contraposition. So here's the idea for proofs by contraposition. We rewrite the given if P then Q statement using the contrapositive. So remember, the contrapositive of if P then Q is not Q implies not P. Okay. Then we're going to act just like we have a direct proof, but just on this alternate form. So we're going to assume not Q is true, and then show this implies not P is true. Note the domain and ensure our computations and definitions apply for the domain. So we're asked to find a proof by contraposition of the statement below. So prove that for any integer x, if x squared is even, then x is even. So we could prove this directly, but we want to start with a simple example that we can use for a contraposition. So let's start by finding the contrapositive of this statement. So here's the contrapositive. We keep the same domain, prove that for any integer x, but we write x is even first but negated. So if x is not even, then x squared is not even. So these two are reversed and they're both negated. Now this may seem obvious, but we should not assume anything. As a fact, and we're going to prove this later, an integer is either even or odd, but it cannot be both. Okay. So that means that we can say that if an integer is not even, it's odd, and we'll replace not even with odd in our statement. That way we can use the definition for odd to help us prove this result. So I put our definition for an odd number here, so it's handy, and here we are going to write our proof. So when all else fails, you start by stating the domain. So where are we for any integer x? So you pick an arbitrary value in the domain, so let x be any integer, and now assume the hypothesis. Suppose that x is odd. Okay. Next, we use the definition of odd to rewrite x in that form. So by the definition of an odd number, there exists an integer k sub 1 such that x equals 2 times k sub 1 plus 1. Okay. I also wrote here what our goal is. Oops, we lost a little bit here. So our goal is to get or to show there exists an integer k such that x squared, because x squared is odd, equals 2k plus 1. So we want to use this information to get that x squared equals 2k plus 1 for some integer k. Okay. So now, using this, we have x, but we want x squared, so let's square both sides of this equation. So squaring both sides, we have x squared equals, note this is a binomial, you need to square it. You can write out the two factors if you'd like, just make sure you don't forget the inner and outer terms, and this is our result. Okay, so we have 4k sub 1 squared plus 4k sub 1 plus 1. So note, let's slide down a little bit, okay, we want 2 times some integer plus 1. So we had the plus 1 here, I left that there. Okay, we have a factor of 4 for each of this. We only need a factor of 2 for this expression. So I factored a 2 out from each of these, and we have this result. Okay, so if this expression in the parentheses is an integer, we're all set. So we just have to state why it is. So we have a sum. We know k sub 1 is an integer. We stated that earlier. Okay. Now we have 2 times an integer plus 2 times an integer squared. So in addition to saying that that the integers are closed under addition, we also have to state that they're closed under multiplication, and then we can state and redefine a letter k that equals this expression. So since the integers are closed under multiplication and addition, and k sub 1 is an integer, this expression is also an integer. Now let k equal that expression in the parentheses. Then we can rewrite x squared as 2 times k plus 1, where k is an integer because we've shown that, which is the desired result. And we've proved the statement.